Okay.
All right, you're good.
Yeah, so welcome to lecture 6. And today we're going to be talking about web servers. All right, so what happens when you visit a website? So before we talk about that, let's do like a brief recap of what we talked about last week, right? Last week we talked about networking. We learned about like networking for all the way from the bottom from like the hardware when each computer has like a hardware address that's called the MAC address. And we slowly like there's something called ARP, which resolves an IP address, which is a higher level address, into the actual MAC address. Uh-oh, the TV crashed again. Can you guys see my screen here? I guess I'll just talk until it comes back on. Yeah, and then we learned about two protocols called TCP and UDP, which computers can use to communicate with each other through their IP addresses. And in order to reach each other by their IP addresses, they go through like a series of routers from the source to the destination. And when you send a single request, it might consist of like a bunch of different packets, and each packet might take a separate path through the big network, the big internet, which is like a spider web. But eventually, it'll all get back to the destination, and those will get put together, right? So building on top of that, right? That's the basis of the internet. So IP addresses, which is internet protocol addresses, and routing. And we briefly mentioned something called the domain name system as well. And the DNS domain name system, or DNS. Oh, the TV crashed again. Well, hopefully you can see my screen here. So DNS, web servers, and load balancing are like the three more things that we need in order to like have a fully functioning website. I guess technically you don't really need load balancing, but it's something that we're going to talk about, especially for sites that receive a lot of traffic. Okay, so first let's talk about DNS. I think we like briefly talked about DNS at the end of last lecture, but basically we talked about how like we can communicate with other computers through their IP addresses, right? So for example, we might have a server that's at 169.229.226.23, right? And this is an IP address, right? And we can reach a server at this IP address through like TCP or UDP or whatever we want, like through the internet. But when we visit a website, right? Of course, like I could go to my computer and type in like a big IP address, but in order to be more friendly, we usually have names like ocf.berkeley.edu or like google.com or like whatever. And in order to map these names to IP addresses, we have another abstraction called the domain name system. So each one of these is called a domain name, and it there's a couple things you can use DNS for, but the primary one is to identify each domain name with a server to send requests to. Right? So DNS is like another protocol that's like we use. There's a couple ways to do DNS nowadays, but like the most like normal one is just like over UDP on like port, I think it's like 53. But the specifics of how DNS works, you probably don't need to understand in too much detail. But the idea is that DNS works on like a hierarchical level. So, right, so the OCF owns the domain, or I guess we don't necessarily own the domain, right? But we have control over the domain ocf.berkeley.edu. So, and we can actually designate additional subdomains under that. And the way that it works is that when you visit a website, your DNS resolver will first start from the top and go all the way to the bottom, which is like from the right to the left of the address. So first it's going to find edu and then figure out who's in charge of the name servers for edu, and then those people will have like a record somewhere, which is berkeley.edu, and then the DNS request will make another request to berkeley.edu to ask for what is ocf.berkeley.edu, and etc. And then finally, when we get to the desired one, then it will finish the DNS request, and then it can send. So now it might get back this IP address from www.ocf.berkeley.edu. And then finally, it can send the actual HTTP request, which we'll talk about later. Let's see, what is this? Oh, yeah. Oh, so this is the diagram of what I was talking about earlier. So first, so your primary recursive resolver is like, usually you don't do all this recursing yourself. You ask someone else to do it, right? So I ask 9.9.9.9, for example, which might be some DNS server, for www.ocf.berkeley.edu. And then it will make a request for the edu subdomain or the edu domain. And they'll make a request for the berkeley.edu domain. And then it'll make a request to ocf.berkeley.edu, and then www.ocf.berkeley.edu. So this one actually skipped a step here. But yeah, does that make sense? Yes, question.
So it uses the information from the previous DNS server to find the next DNS server.
Yeah. So there's a couple of different, well, right now we've talked about DNS as like this like abstract concept, but how it actually works is that you can specify a bunch of records in DNS, and there are like some different types of records, but one of the types of records is called an NS record, and that's basically saying, instead of telling you where this domain points to, I'll tell you who to ask.
Oh, yeah.
Right. So edu probably has a NS record for berkeley.edu. So it'll follow the NS record and make another request here. Yeah. So it's actually, on this diagram, it starts at edu, but actually this domain, www.ocf.berkeley.edu, it actually ends with another dot. So turns out the very, very, very top level is like dot. So the dot domain is like the top level name servers of the like entire internet. So in order to figure out where to ask edu, where to get in order to figure out who to ask for edu, it first asks who to ask for dot. So that's like another tidbit that's pretty interesting. Yeah. Oh yeah, fine. Okay. Yeah. So when you request ocf.berkeley.edu, it'll send an NS record, and it says the name servers for that name live here. And then it'll request that. Okay. So here are the aforementioned types of DNS records. So the first one is, this is like the most common one, which is an A record. It's just saying that this server is located here. And that's like the very bottom level. So that would be like www.ocf.berkeley.edu has a record pointing to this IP address, and then .23. Similar to that, there's also quad A, like, or AAAA. That's the same as A, but it's for IPv6, which is like, we talked about this last time, but it's like the new internet version, internet protocol version, because we're like running out of IPv4 addresses. Actually, we've already run out of IPv4 addresses. So in addition to A and quad A, there's CNAME records, which are basically like, CNAME stands for a canonical name, and it's basically creating an alias. So what's an example, right? If you have, I guess an example we have at the OCF is we have our app hosting server, or we have like names for each actual server, right? So for example, we might have a server in there called, I think our servers have like a naming scheme named after like disasters and stuff. So we might have a server called vampires, which has the A record. But in order to like abstract on top of that, we also sometimes have CNAME records for like a more descriptive name. So for example, apphost.ocf.berkeley.edu has a CNAME record pointing to vampires, because that's the server we use vampires to do our app hosting service. And there's also like, for example, like ssh.ocf.berkeley.edu has a CNAME record to tsunami. So, and for CNAME records, is always that a name points to another name. So after you get a CNAME record, you have to do the whole thing again to get the new one. And yeah, so to resolve A records and quad A records or like all the other records, if you encounter a CNAME, you just follow the CNAME until you get to one of these actual ones. There's also MX records, which is for mail, or I guess email. Email actually predates like the web, which is like the web as in like websites came after like email existed. So before that, we would use MX records. And this is like, mail for this domain should go to that server. So on my domain, I might have an MX record pointing to Google servers to tell anyone, any mail servers sending email to me to send it to Google servers. And then NS, as we talked about before, is just like storing the what's called the authoritative name server for a subdomain. So yeah, so OCF.io, which is another domain we own, has an NS record that points here. Basically, it's just saying that if you want to look for any domains under OCF.io, you should ask this server. Does that make sense? Any questions about these? Okay. Yeah, so that's DNS. It's pretty cool. It lets us not have to memorize a bunch of IP addresses. And it also lets us, like, if we switch out a server, we can change the DNS and then everything will still work, right? If we had a list of hard-coded IP addresses, then everyone would have to update their IP address anytime changed. And that's like not really feasible. Yeah, question? This one?
What's happening on the right voice?
Yeah. So this server in the bottom right is the authoritative DNS server, which is like the actual OCF name server, which are like in the server room somewhere. I think the green arrows are just like the answers. So the cyan arrows are like question, and then so it's like question, answer, showing the flow of information. Does that make sense? The arrows are a little confused. Oh yeah. What exactly is happening here? So okay. Yeah. Okay. So this recursive resolver gets the edu and then it gets berkeley.edu. And I think Berkeley actually does something special. So instead of just setting, I didn't realize this at first, but I think instead of just setting like an NS record for OCF, it does its own. So Berkeley has this server as actually authoritative. And then they just like delegate to us on their side instead of like sending back an NS record. Does that make sense? So that's a special case. So Berkeley pretends to own the DNS, but they actually make another DNS request. So you can have like different kinds of layering. This is a campus DNS server, the one on the top right. Let me see. No questions on Zoom. Okay. Oh, a couple more. There's TXT records, which are like just any text. They don't really mean anything on their own. It's only like if we assign meaning to them. So like one common thing is like if I want to add my domain to Google or something, they'll usually ask me to verify it by adding a TXT record. SRV is a weird one. Basically, like there's it specifies a host and a port for like specific services that are running, right? Usually DNS records, for example, like the A record, they only resolve like a name into an IP address, which is like of a server, but it doesn't tell anything about what port on the server it's running on. So for example, if we're running like Minecraft on port 3000, the default port for Minecraft is like 25565 or something, but let's say we were running it on like 30,000, which is not the default port, and we want to tell Minecraft to use that port. We could add an SRV record under like, I think it's like underscore Minecraft dot underscore UDP dot the actual name that points to the host and the port. So we could specify the port in the request, in the record. They're like kind of not really used very often these days, but yeah, they exist. The important part is the port itself. It stores the port. And the last one on this slide, which is the SOA record, it just stores like information about a domain, like who to contact. Yeah, I mean, it says here how long the server should wait between refreshes. Technically, it doesn't like do anything, or like it does. It only like technically you don't need one for it to work, but like to be compliant with like people's requirements, you should have one. Yeah, but I guess it's unlikely that things will break if you don't have one, but you should have one. Okay. TTL record. It's not actually a TTL record. It's like some records you can put a TTL on it, a record. So that just tells clients, well, it tells people how long they should cache the DNS result for. So if you have a very short TTS, it means that you can change the DNS and then people will get it updated a lot faster. But it also having a longer TTL, sorry, did I say TTS? Having a longer TTL would have better performance because people could have it cached and faster. Because like, remember, if we have this big diagram, it's like there's so many requests and there's caches at basically every step along the way. There's even one on your computer. There's one on probably your router. There's caches everywhere. So it does increase the performance a lot. Okay. So just around DNS, there's like a common, or it's not common, there's a type of attack called DNS poisoning, where essentially if an attacker gets access to like one of the DNS servers or somehow finds a vulnerability in one of the DNS servers, it can do DNS poisoning, or it can like, so let's say this attacker got between me and my DNS server, and it like intercepted the request and then changed it. So now when I visit ocf.berkeley.edu, instead of giving me the right address, if the attacker might be able to spoof this other one, I would visit like a different website instead. I think, I don't remember how recent this was, but sometimes there's like vulnerabilities in DNS servers where even if you can't like get between them, sometimes you can like do something weird to have your DNS request be cached incorrectly, and then people can exploit that. I can send like a link if someone wants more information about, like, there was something that happened, like, I don't know how recently. I don't think it was that recent. But yeah. So here's another one. Wait, what is this? I think this is just the same slide as last time. Or yeah, if an attacker gets access to like a DNS server. And if we have the big diagram, the poisoning can happen at any point along the way, which is why it's like, oh no. Which is why, like, if you're configuring your DNS, it's a good idea to make sure you trust your DNS servers. Like if you have it set up on like your like little brother's DNS in his room and then he gets hacked, then like that would be bad. So trust is very important here. So especially if you're authoritative for a lot of people under you, then you should be careful. Yeah. Yeah, and just another note on DNS poisoning. There's like more modern ways to do DNS nowadays, which is like, for example, like DNS over HTTP or DNS over like HTTPS, sorry, which is, and a lot of those are like more secure than like the default UDP way of doing DNS, which is like really old. So some of these attacks won't work if you use like those cool new ways to do DNS. Yeah. Also, if you just use like HTTPS in general, then even if you get the wrong IP address, it won't verify like the certificate properly. So, but yeah. Okay.
All right,
I think Michael will talk a little bit about
web server time.
web server.
Yeah, so basically a web server is a computer running a program. So there's like the server, like the physical server, right? And usually it runs like a web server, which is like a program that also serves information. It's like Nginx or Apache are like two notable ones you may have heard of and probably will work with in the lab. There are also server programs like Flask, which you may have used, Django. Those are all like Python ones, or there's like Swing, Java one. Starts with an S. Spring Boot. That's right. Yeah. No. Anyway. Yeah. So that's how you can have like a Dell PowerEdge server running an Nginx server with a Flask server behind it. So like it can refer to like many things. But yeah. On the most simple level, it's you send a request for information and then it'll return a web page. Usually like the web page is made of like many different things. So like it'll like if you ever go to like okay, so like if you go to like YouTube, for example, and you open like inspect element and you go to like the network tab and then you like reload the page, like you can see like many different things like being served back to you like at different times. And those things will all have like different content types. So like some of them will be like an HTML page, for example, right? Some of them might be like a video, some of them might be like just like XML data, some of them might be like JavaScript, right? So and like your web browser basically does all the work of like building that into like the YouTube experience. But yeah, it like you'll send it requests for information and it will return like basically what you requested. Oh, and I guess we'll just talk about scaling now. So basically what happens when you have like a lot of people querying a web server at once and you have like constrained resources, right? So there are two ways you can scale. Oh wait, we haven't gone there yet. This is just the same picture. Yeah, there. So you can vertically scale, which is just have a beefier server with like more cores and like a higher bandwidth Ethernet connection and all that. Or you can horizontally scale, which is just have more servers. But the problem is like the user won't know like which server to ping, right? So it's like you can, like let's say like with YouTube, right? They're not going to have like YouTube1.com, YouTube2.com, YouTube3.com, and you just have to like go to whichever one like is the fastest at the moment, right? So that's why we have a thing called load balancing, where you put a bunch of servers behind one server, and that server that you send the request to, the outside facing one, like won't even look at the request, and it'll just like have some, or maybe it'll look at like just like some very like small amount of data in like the header of the request and make a decision. So like it won't do any of the actual like processing that your application does. So it won't do like database queries and like any like actual computation usually. I guess we'll wait for this to reboot.
The TV is kind of
Dot. There we go. Yeah. So there are like different like methods for like load balancing. Round robin is like a popular one. Another one might be like it could like you could take into account things like resources on each server and like how much usage each one has and like have like a more intelligent algorithm for like load balancing. But yeah, round robin's like the most obvious, which is just like in order you just like fan them out like that. So yeah, that's a visualization of many people querying your load balancer. And maybe like this guy's request will go here, this guy's request will go here, and this guy's request will go here, right? And this server doesn't really do any of your actual like application logic. Yes. So you have different algorithms. Do you know what the static algorithm is? Okay. Well, yeah. Okay.
It's just saying that it doesn't depend on. It's static versus this one's dynamic.
I see. In what way is it dynamic?
If it's based on response time, it's like the load balancer like dynamically adjusts.
Okay, well, yeah, like you can have like different parameters that will go into your load balancing algorithm, and response time can be one of them. Yeah. So, oh yeah, so they ping like all of the like servers that are connected to them, like the load balancer will do that. I think this is just true of like anything where you have like many things that need to be working at the same time. Like RAID controllers for like hard drives will do the same thing, where it'll like check to see like which of them are functioning properly, and then it'll only like make use of the ones that are functioning properly, and it'll like alert you if one of them goes down. So yeah, like one of them goes down, then you'll know about it, and it won't route any traffic to that server behind it because obvious reasons. And that is the last slide. So yeah, I mean, any questions or yeah?
It's like a really, really large scale. Like if you have like whatever Google, like will surely have like many load balancers? Like is it like trained load balancers? How does it work?
Oh, I think they have like a sort of like tree of load balancers, something like that.
Oh, okay. But it's just yeah.
I mean, they like that's getting to a level where you have like they'll do interesting things that most people don't do, I would say. Like, will they have many load balancers like chained together? Which I think the answer to that is yes, but
At some point, your load balance.
yeah, that's true of anything where it's like many things that need to be accessed like in a tree fashion. Like page tables and OSs are like that. Like many things are like that. But yeah, I think load balancers are no exception. That is a recurring theme in computer science. Any other questions?
Like another tool that you can do with load balancer is like if you need to like make an update to your application with your server, if you only have one server, then it requires some down, right? But with like load balancers, if you have like 10 running, you can like take down 5 of them and put on like 5.
Yeah. Yeah. See, yeah, you can like slowly rotate out like the ones with like an old version of your application, and then yeah, put new ones online. So indeed. Yeah. Any other questions? Or yeah. Nginx is like a general purpose web server slash like load balancer. So like Flask uses what's called like WSGI, which is like a system for basically like a Python program to like listen to web requests and like respond. So like with a Python program, you can handle like very complex state and stuff, right? Whereas with Nginx, it's like just meant for like I guess you would say like boilerplate or like kind of top level. Like Nginx is like a much more thin web server than Flask, to put it simply. Like like Nginx can't do like application state and like computation, like write to your database and like anything that you would actually need for like a web app, right? Like Nginx just like sits in front of your Python server and like load balances between them, or like Nginx, like you usually have like a very short, like, maybe like 50 to 100 line config, maybe longer if you're being fancy about it. But yeah, like it's not going to do anything like fancy that Python can. It's just like one program that you give like very few parameters to like do a simple task.
It's like very fast.
Yeah.
So, like if you just need to serve some static file or proxy.
Yeah, proxy, exactly. Yeah. Whereas Flask is like an actual program. So
if you take CS162 one of the homeworks is like you write an HTTP server. It's actually not that complicated. It's just like you send some text. It's like a lot of these like old things are like they seem very obvious now, or they seem kind of weird, like dumb now. But it's like you just get a request and you send back a response saying like HTTP/2.0, and then content type, and you just send the data. It's like, it's just TCP with a specific one.
That's like commonly agreed upon and standardized. Yeah. Yeah, I think like if you ever make like a web app in Python or like with JS, like you'll probably see like a lot of this. If you ever have to like host it on a server, like you'll usually have to do that. Like you'll have to like set up your DNS records and Nginx and like put it behind a firewall, stuff like that, maybe. But yeah. Like I think that's probably like the best way to learn about this is like you're like getting intuition for like what it looks like is to do that, which I think the lab will have you do. So I don't know. I have to leave like soon TM, but yeah, I think it's just like it's probably like setting up like Apache or Nginx, I'm guessing. But yeah, I think that concludes the lecture, unless anyone has any more questions. Okay. Yeah. Stop share.
I slept until like 2 a.m.
Okay.
I had some sleep. Yeah, fell asleep and everything.
Hello, Jason. Are you still there?
Yes, I
Hello?
am.
Okay. Yeah, we'd like finished talking and stuff. So
Oh, okay.
Blacked out.
Sounds good.
I was in like another DeCal. Yeah. Yeah, it's